Okay, I appreciate you guys allowing me to talk about this. And so, really, this is the second of 6 lectures. And following mine, Barbara will discuss inverse theory and tomography. And then I'm going to do a follow-up to this lecture, which is a more application. So this lecture is fairly introductory. And then we'll go through lithosphere and attenuation, things like that. So I wanted to do a little bit of an anatomy of what I took on as my task here. So anyway, body waves, these come out of solution to the wave equation. These travel into the body of the Earth. This contrasts from Gabby's description of normal modes of the body vibrating. I mean, these make up these things, as well as surface waves that are due to contrasts in properties. The Earth's surface is a big one. So, observational, I take this for me to mean this is very careful analyses of data that we collect, and we compare these things to predictions of some form, some measurement of these data. It doesn't preclude tomography, this thing I call observational seismology, but the material I've taken to present today is not necessarily tomographic results. In introduction, I have 60 minutes to talk about things. I'm going to talk about things that I think are important for seismologists as well as non-seismologists to understand some of the things we assume. And I learned something on Monday morning that I have a much easier job than Dr. Laska. Okay, so what am I going to do? My focal points are basically, let's see, I'm going to spend like maybe 20 minutes on terminology and basics on things that people who study body waves in observational sense depend on. I'm going to very briefly talk about some types of data and examples. This is going to be very subjective. It's kind of what I found on my laptop, because in my next lecture, I'm going to do some more observational body wave vignettes that give models and hence interpretations. And so what kind of things do we actually measure when we look at body waves? And there's a collection of things here. So I will briefly go through some of those. And then from these measurements, we do analyses. And these often include some kind of predictions to compare to our data. And then higher order methodologies. And then, of course, we get to our results and our models in which we run wild with interpretation. So this part is really important. I'm not going to spend much time on this today. I will, in my next lecture, where I hone in on some examples, and people have been mentioned some things over the couple days, and so I wasn't really sure what things I was going to focus on, but I'm getting ideas from conversations, and I may focus on lowermost mantle and outermost core. I could also do upper mantle, but the things that we interpret often depend on some of these very basic things that get swept under the rug. Okay, so I got a couple images that I put on in the fall CIDER workshop. That here we are today, and for sure, seismology images Earth today. And so the question regarding how might this relate, here are these things, of course, moon's much further away, to deep time. Here are some, kind of cartoons and models of Earth today. And so we want to know, and Mark mentioned this in his preamble on day 1, how can these structures relate to phenomena of the past, whether these things are primordial or whether these things are processes that have been built or leftover things or are being created today by dynamics that are remnants of structures in things of the past. This is an important question. When I was first invited to participate in this, I thought, wow, seismology in deep time. That's special. But in thinking about it, it's really, I'm going to kind of get up on a soapbox and say, you will know nothing about deep time of any planetary body without detailed imaging of this interior. And if you want to battle me on that, let's just compare Venus and Earth in mapping out evolutionary pathways. We need the structure. So, okay, so this is the first part of my talk. And there's been enough pictures of things like this, so I'll go really quickly through this. And I hate it when people have too many slides and they go click, 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 click. And so here I am. I just wanted to make the one comment that in seismology, maybe this isn't so much these days, but body wave seismology, we often distinguish what we call source seismologists, people who have something to do with the path, and receiver. Receiver could include instrumentation, it could include crustal or sedimentary structure or lithospheric structure. The type of observational seismology, body wave seismology that I'll be presenting has to do with the path, where these body waves go into the interior and they sample structures along the way, and we try to decipher that, the receiver. I don't make a big deal about it today. I'll talk about it a little bit next time. But you can't avoid the source. And in fact, the source and source structure, like if this earthquake is close to Earth's surface, you have energy that will propagate up and then down. And these kinds of things very much are in our business when we try to image the interior. So we have P waves, we have S waves, we have surface waves. Gabby showed all this. There will be terminology that I'll forget that I'm saying. I just want to make sure when I say great circle plane, it's the plane that includes the source and the receiver and Earth's center. And the great circle path is the surface manifestation of that. So I may blurt those out. We also talk about azimuth and back azimuth. This may mean different things for geologists and seismologists. The azimuth is something that references from north in this great circle path. From the epicenter of the earthquake, the back azimuth is from north to the great circle path, always clockwise at the station. And then there's this thing called ray path, and I'll show a few slides on that. But this takeoff angle of the ray path is something we use more and more these days. And I'll talk about that briefly. Okay, there's different kinds of energy. Here is the ray path, this green thing. Here I'm highlighting the two types of shear wave particle motion decomposed into a horizontally vibrating shear wave and a vertically propagating shear wave. That is, both of these guys are perpendicular to the ray path. The ray path is the normal to the wave front. And these will get used, one or the other, in specific studies aiming at something in detail. And those I will, they will manifest in this talk and in my Thursday, or next week, Tuesday. So we have an earthquake. We have longitudinal motion from the P wave vibrating. This is a 2D world. We have the shear horizontal and the shear vertical in and out of the board. And we, I can't draw parallel lines apparently, but we have, so this would be something we define as a transverse and radial direction, but we have our seismometers, three orthogonal component sensors in the north, south, east, west, up, down direction. And so it's an easy deal of taking these north, south, east, west and rotating them to the great circle plane in order to try to see these guys decomposed. And so there was a question in Gabby's talk, I think, about that. So often you'll see RTZ on our slides, which radial, transverse, vertical, and ZNE for up, down, north, south, east, west. Now, just very quickly, this R is a little bit of a funny business because the horizontal components of vibration are in the surface, but if a wave's not coming straight up, then this, let's see, here's my ray path, and here's shear vertical. When you get to the surface, the radial, the R, is the horizontal component of that. So sometimes that gets a little bit lost. Okay, more. They are orthogonal components of motion, but R does not equal SV. Okay, so more Seismo 101. This is from Lily's geophysics book. Just like in light, changing medium properties bends waves. This is important because, in our spherical planet, whether we have constant property layers with interfaces, and lets you do your Snell's law, or gradational properties, for a given seismic wavelength, you could always divide the planet up in a predictive sense in constant property layers and employ this kind of technology. And this is really what we do. And rays will bend accordingly. And so, as I said, we have this thing called a ray path, which is perpendicular to our expanding wave fronts. And so in a lot of our diagrams, we just draw the lines because it's much easier when you're talking about complicated things to the Earth. And maybe it's curved, whatever. So this energy from some source, whether it's a hammer in an exploration experiment, or a meteorite falling from space, or earthquake, or the nuclear bomb testing, and through the 60s and 70s were sources of energy used in Earth studies. You have these expanding wave fronts. They go in, they bounce off things. Anything of contrasting elastic properties is going to affect these waves, whether it's merely bending them and reducing their amplitude, or providing enough of an interface that reflects energy, which we study. So there's a couple nice animations that Mike Thorne passed along. So I'd like to show those. So here you see both the wave front. This is the red and blues are ups and downs polarity predicted, and the ray paths are just perpendicular to the wavefront. And this is showing the core reflection. Here's the core. This is just SH, so the particle vibrations in and out of the screen here. And so you can see there's all kinds of stuff going on, but this is specifically the core reflection. So I'm just trying to emphasize, I'll be drawing ray paths and not wave fronts, because wave fronts are complicated. Here's one if you want to study the upper mantle. This is a phase du jour, SS, which is bounces between the source and your point of interest one time at the surface. And so this guy gets used a lot to study the upper mantle phase boundaries, and more recently the lithosphere. So I think these are really good animations for demonstrating the difference between ray path and wave front. Okay, now you could see that there's all kinds of stuff going on in here. Anytime you have any contrast in properties, you have the opportunity to reflect energy or convert energy. SV and P waves can convert into each other. SH waves stay SH. And so this is taken from Mary Fowler's book and just some annotations. But you always have the opportunity to reflect or transmit energy. For SH waves, it has to be a solid to sustain a shear stress. So any sort of fluid terminates this, and like this situation would be the core mantle boundary. And that's why SCS off the core mantle boundary is often used as SH waves, because you get total reflection and they're really easy to see. So with the P wave, you get both types converted and reflected. So this makes for potentially a messy situation for some types of waves, not for others. But all of this really needs to be considered, especially if we're worried about amplitude of energy. And feel free to interrupt me as we go. Oh, a question.
Why are SH and SV so different? If you have a P wave carrying SV and not an SH.
Okay, the question is why are SH and SV... okay, like if I'm coming down to this table as an SH wave with lateral particle motion, I bounce off. Let's say it's fluid below that. I can't, with this lateral motion, I have no up-down stress to push down, which I need. I need to have motion in this direction to have a longitudinal wave keep going, which would be a P wave. And if it's fluid, there's no SV energy. Okay, so basically you think about it as particle vibration and what's going to communicate a stress across the boundary. Okay, this is, some of you may have suffered through my tests to name seismic waves. You guys have probably already all taught this, so I just want to make sure we're all on the same page and have it on a slide. But we name these guys successively. It's kind of like our genome sequence, which is a short one. P or S means P or S in the mantle, because waves that are going through and bouncing all around, we just keep collecting letters. If it's in the core, K. Gabby, you can tell us why a K, right?
Yeah, no. Cam is the German word for core.
That's right.
Spells K.
There you go. And so only P waves in the core. The inner core, if it's transmitting, capital I, capital J. Reflections, small I. So you'll hear us say, oh, P little I or big I. We're talking about these guys. Anyway, so I'm just going to show a bunch of these. So now we're just looking at ray paths, not wave fronts. And I'll show a bunch of P waves. This is one that gets used a lot for deep mantle study because you're reflecting something off the core boundary and you're comparing it to a mantle path. This is something that seismologists do that may or may not be apparent, is we often have a reference phase. Now I'll revisit this a lot. By reference phase, I mean here I am out here at 70 degrees, and I vibrate as these different waves come to me. P wave gets there first. I want something that I could say I think I understand before I go to study the thing that is the structure of interest. So if I'm here and I see this blue P wave ray path, and my P wave is very simple and understandable, I'm like, great. I think I know what the earthquake looks like in this, manifestation of the surface shaking, and then I can go and hunt for this reflection. So we often need some kind of a reference phase for travel time, because if my P wave gets there and it shows up when it's supposed to, I'm happy. And then I see this red thing come and bounce off the core. It gets up there, and maybe it arrives late. And so I'm like, well, that's cool. So this red path had to be delayed somewhere where this blue path isn't. Now the dirty laundry in seismology is we assume we take the difference of those times and we analyze the differential time. And we put it in our structure of interest down here. But you could actually see these paths bottom far enough up off the boundary for in the forward observational body wave analysis sense, you can kind of goof up, and we do. Okay, so here's my test. What is the name of this phase, since I just gave you the key? I hear a rumble. I need some signal to noise ratio. Bruce, what?
Yeah, I think that must be PK little.
Ding! Little c for the core mantle boundary, little I for the inner core boundary. Very good. Okay, these phases get used for the outer and inner core, mostly the inner core. Now, you see, like, wait a minute, I didn't see any ABs or BCs in your legend. And I'm choosing not to go into this in this talk, in slides and stuff, and it may manifest in my next talk, but that's for a triplication, a classical sense of a layer over a half space. You have the reflected wave, you have the head wave. Well, the seismologist but he's going to put it on his board. It's not in his slide. When you have your distance and those of you over there, sorry, you have these, there you go. See it? You have these different arrivals that are predicted to come, like one that's traveling in the layer, one that's reflecting from the layer, one that's going underneath. It's called a triplication, meaning there are distances where you actually get 3 arrivals. And Bruce Bolt, I remember when I took my first geophysics class, he used to talk about triplications and caustics in regards to light going through a glass of beer and the reflection it makes on the table, and I was very impressed with seismology and beer. So anyway, so in the great creativity of seismologists, there's the A, B branch, B, C is reflection, C, D is the refraction, and that's where these guys come from. And I could come in after my talk and say, I want you to spell this out more, and I'm happy to. But anyway, you have, and there's one that goes through the core, which is called DF. So there's more exotic things like this, and you might think I've kind of gotten a little crazy to show this, but people are starting to analyze these things. Like here is the one P4KP. This has actually been used for decades, infrequently, but waves that go in and they start bouncing 1, 2, 3, 4 legs of this thing. It comes out. This is cool because there are distances where the mantle paths are really similar to the core reflection PCP. And so again, this business about needing a reference phase, this can give you interesting things about attenuation in the core. Okay, so here's my last test. What's this phase called? This is basically just a ray prediction. This is freeware tau p path. Actually, you could get these things off my website. Let's see, let me pick a pill. Should I torture you? No, I won't, because you are not allowed to ask me about an isotopic system. So I'll leave you alone. A little c? A little c means reflection off this thing. Dave? Right, okay. P, right? K. Oh, it's going in. What kind? Little eye or big eye? You always have to say little eye or big eye. Big eye. Big eye. Oh, but look, it's not coming out. No, it's an underside reflection. We don't give those a name. We just add another letter. Okay, check it out. P, K, correct, little eye. And it's going in the interior. Hey, I've been watching you guys change your story for decades, but we have not changed. We have not changed the naming of these phases. Okay, big eye, right? Sorry that I said that. I sometimes get dyslexic in front of people figuring things out on the board. And then another big eye because it bounces and keeps going. KP. So that's right. So this is PK big eye or PKII KP. Now you might think this is a little like wow that you're appealing to really crazy stuff, but Feng Lin Niu had I think it was a Nature paper on this guy recently. It's very hard to see. We looked for 2 years for this for far side reflections, and out of 1,000 earthquakes, we found 4 of them. That's not enough to publish. But I thought if near vertical incidence, which is very sensitive to the reflection coefficient if the inner core boundary is fuzzy, let's do that as a function of reflection angle. So this phase actually, it could tell you a lot of these things you want to know about the base of the outer core, because that's going to affect this reflection coefficient, because it's elastic structure, or blurriness of the ICB. Okay, back to the mantle. These multiple S paths. The surface is a very good reflector for horizontally polarized shear energy, because it's either air or water, neither of which support SH waves. So these guys just keep going, and eventually, as Gabby noted, they become your love wave in the limit. And we have something that we call the major arc and minor arc. The minor arc is the less than 180 distance between your source and your site, and the major arc is a long way around. So these guys are very good for, they're used in tomography. They're used for hunting for layers in some case. They're very clear waves, very easy to see. Okay, a couple of core equivalents. I think I'm spending too much time on these. You can get more exotic. Here's major and minor arc of this phase is another very well-recorded phase. Very easy to see. You could add bounces. They get a little crazy, but one could hunt for and find these different paths. The ones that are skimming, and these are just 5 random sites I picked. More typically we have one receiver, and you're looking for all of these guys. Okay.
S shouldn't go to the output, correct?
S. Oh, I'm sorry. It has a K, which means it's a P wave in the core. So which therefore means the mantle portion of these guys is SV. Vertically polarized, it comes down, and boom, I can convert to the P. That's right. Thanks for helping me with that. Okay, I'm going to leave the ray path for a while. If you have any questions, this is your chance. M. Yeah, we got tired of writing the multiple Ks, and also with the 3K being kind of an undesirable sequence of letters here in the States because of some racism stuff. But it's easy because now we're getting to S4K. S is not uncommon, and actually George Helfrich recently published a paper with S5KS, and it's sort of like, give me an abbreviation. So M is the number of Ks.
Earlier you had an II. You don't call it 2I?
You could.
Okay, so it's equivalent.
Yeah, but you have the same number of digits, so we just keep II.
Okay.
So it's like,
It doesn't
what?
save anything.
It doesn't save you anything. It doesn't save you ink or forearm muscles. Okay, anything else? Okay, I'm just going to really briefly talk about radiation pattern and this idea of quadrants of different types of motion stress. Here's my platonic fault block, equivalently double couple set of forces that will result in dilatation or tension quadrants and compression. And this has a predictive, this is kind of annotated from Peter Scherer's book. This is one of my favorite figures in that book, that I added the equivalent sliding planes where along the planes you're predicted to have, this is at the source, and these arrows are representing amplitude of motion and direction of motion of a particle in the far field. So you have nodal planes. You have maximum regions of, this is for longitudinal, so actually P wave, stress, motion. So why is this important? This is important because if I'm an earthquake and Dave Stevenson is a sensor, and Curtis wants to study the data from Dave for a core reflection, but my fault is precisely like this. I break. Theoretically, it's zero amplitude there. And you might think, well, that's predicted there. But now, as we're learning in the earthquake community, at least great earthquakes are showing multiple faults and segments. And so you could have a bunch of these kind of superimposed on each other. Or it could be that my downward energy to Dave for a shear wave is zero, but my wave that went and reflected off the surface and went down is actually strong, because you could be in a node for your downgoing energy and not for your upgoing energy. And Curtis is actually studying something that dealt with the crap of everything in the crust that's interesting for those who study that. But if you're studying the deep earth, it's muddled your data. So this is very important. Now, we often have these beach balls. We call them beach balls, but I like to call them beach bowls, because these focal mechanisms that you see on maps are the lower hemisphere. So I torture students with drawing bowls for thrust, oblique. Anyway, but that's just P wave motion. You have your SV and SH, and so this is again lower hemisphere. Like, here's my source, and a rupture happened, and at the source infinitesimally we talk about the amplitude of SH, SV, P energy at the source. This is really important. Seismologists, we've often kind of got around it by trying to study reference phases. We say, oh, they're close together, but actually this is in our business, and we have to pay attention to that. So basically, this may or may not radiate energy of choice, P, SV, or SH. At the ray parameter, I don't think I introduced that. That's the constant thing along the ray. Comes out of Snell's law. It's basically angle. and the region of interest. Fiji Tonga earthquake, and you want to know about the large low shear velocity province beneath Hawaii. That means you're recording it in North America. Well, maybe it didn't actually radiate anything. So, and then the amplitude may be varying across your array of sensors too for your phase of interest, but maybe not your reference phase. So that's a challenge. We have to worry about that. Okay, so now you think you got all the do's and don'ts, and you want to study beneath the African craton. So how are you going to do that? Where can you seismically image? And I'm including three things here. You know, your geographical region, maybe it is a geography, or maybe it's a tectonic. You want to study all slabs, or you want to study all ultra-low velocity zones, whatever it is. Some those aren't tectonic, but or maybe it's a depth shell. What are the things you need to worry about? Well, first, you have specific corridors that you can image using body waves. Now, normal modes, you sample the whole volume, but we have specific earthquake belts and sources and specific receivers and receiver arrays, and so we're limited to what volumes of the planet you can study. And you also have to worry about the seismic wave path, obviously. If you want to study the core-mantle boundary underneath Canada, you're screwed. Well, probably. Because you need to get something down there. It depends on the type of energy. So there's certain parts of Earth that remain opaque to certain wave paths. Other wave paths, I could study underneath Canada actually with core diffraction. But those are going to be very long paths and average over some distance. But if that's all I can do, I'll do it. Okay, so you have to worry about that. Let's say, I said there's no more tests, so I won't ask the question. But let's say your thing is right beneath the 660. Or your thing is right on top of the core-mantle boundary or beneath the boundary. So you could say, okay, and just for fun, let's say beneath Hawaii. See, I want to look at. I know the 660 is upwarped if I'm warm there, and so I'm going to look for the plume. Or someone says ultra-low velocity zones migrate around to beneath upwelling, so I'm going to look on the core-mantle boundary there. What seismic waves would you use? There's two issues. There's which seismic wave samples this volume, and then there's, do I have the right distance between receiver and source to get there? And I'll just show some quick examples. If you really wanted to study the upper mantle phase boundaries, you could look at these precursors to SS. And actually, this will get you to Hawaii because you have Southwest Pacific earthquakes and Canadian stations. You have South American earthquakes and European stations. You can do this. So a really long path. They tend to be long period energy because long paths. You could also do it with, say, P prime.
And comment a little bit more on the period path, like something that hasn't come up yet.
Yeah, I was going to sweep it under the rug a little bit, and I have a later slide saying that the period of your energy determines the minimum wavelength that you can hope to study of structure. And period choice is often based on, in these body wave analyses, what is the smallest period of which that I think I understand my data. Because if you take, I have a very high quality broadband instrument, and here I am in, eastern U.S., and I got my Fiji Tonga earthquake, and I'm looking at SS broadband. You have everything along the pathway there, and I'm hoping for like this, utopic Gaussian, quick stress release earthquake, but no, it's bumpy and crappy looking. Well, what is good and bad looking data is sort of a subjective business, but so I low pass filter it to make it smooth, because really what I want is data from my different earthquakes to be similar so that I can include them in some batch processing to do analyses. And so for SS, with these very long time paths, to get the waveforms similar, people have low pass filtered them at like 25 seconds or 30 seconds, which means when you figure out what kind of Fresnel zones you're dealing with here, you're imaging structure at like 500 kilometer lateral wavelength. We would like to go shorter and shorter and shorter period, but we run into a problem without enough data sampling the volume. You can't determine where your shorter period information is coming from. It's a really big deal, actually, this question, and I was going to address it more in my next lecture. So anyway, P prime precursors. There's a ton of other ways: receiver functions, upper mantle triplications, multiple S and P waves to study these upper mantle discontinuities. These guys, this is really interesting. We're working on this now. We're regularly challenged by these data, and that you tend to see these discontinuities at short period energy, even when the data are quite good, when the long period information is there. And this would be more the exam question at the end of my lecture. I could. Why would you not see long period energy of one of these reflectors, but you would see short period? And I could fashion a pretty good question. The core mantle boundary underneath Hawaii, there's lots of core reflections between Southwest Pacific and North America for these things. P going down in the mantle, core reflection, P in these guys. These are good over some period range, and they're used quite a bit. Here's the path. And so again, you have this business of the reference phase. Am I really studying right there, or am I studying some integrated path? This is an uncertainty one has to worry about. So I put here like necessary ingredients. This is just some. You need to be able to illuminate with seismic energy this region of interest if you're worried about geography. If you're thinking, oh, global, I want average properties, then this is less of a big deal. You just have to carry the blind faith that the geographies you do sample don't bias you. You know, we have this religion in our community which is called PREM, which is for, I was so happy like in 2011, Adam, I was telling people 30 years, this is great, and it's actually still an amazing model. And from the core mantle boundary down, there were some data used, and these data are path specific, so you have structure and different paths folded into the model, but it still has survived. But if you're going to do a global study, you have to be sure that the areas you do sample aren't so biased by structure that you're getting the wrong thing. So you have to get to the depth shell of interest, and you have to make sure your reference phase is a reasonable one. And my quick slide kind of addressing Michael's question is, the frequency that you're going to study is obviously going to relate to the minimum wavelength you can see. Okay, so I'm going to very quickly show you some data, like just only two types of data that are commonly used right now. One of them is broadband data. So this is some earthquake that happened earlier this year. This is some of the mess I'm going to present in my tutorial, so you can make these plots really easily. So you have some earthquake, and this is just brute force. Tell IRIS, the Incorporated Research Institutions for Seismology, to give me all their data. And this one brought back 992 seismic stations, 3 components of motion in each. And these are color-coded for epicentral distances. This blob here is a US array, which is Earth scopes, 500-ish stations. And then you get a plot like this. Now, this is a little bit of a cheating plot, because if I plotted all the records, it would be black. These are up-down, so this is vertical motion, and I low-pass filtered it like at about 20 seconds. And this is, the better part of an hour, and this is epicentral distance from at the earthquake to the other side of the globe. So what is done here, so it doesn't look so messy, is if I have a lot of data, I'll just add them up. And this is how many data were added up. So in this US array, central US, we're adding 30-ish records for each line here. But it lets you see the arrivals. So this is just quick, dirty viewing. Are these data good? And it's interesting. There's a lot of things there. Anybody in the room could see that there are trends of pulses going across this this network of sensors, and you can make predictions.
Can you go back? There are a few places there that just look completely anomalous.
These?
At about 50 degrees for those two.
Yeah. So this is something, I didn't sanitize this. This is just everything that came. And they're like this. What's this? First of all, we'll collect the data for a predicted amount of time in front of the P wave. So you could see these lines are all perfectly straight, and then all hell breaks loose for some of these. Some of these are just bad data. It's either a bad... Now, I've not dug in to see, like, what's wrong with this guy? Like, this is quite far away, and so this magnitude 7 earthquake, it could be that the radiation pattern for P energy is not that good. So the way we plot these are like, there's a maximum and minimum amplitude, and you just fill it up to that. That's like the normalization thing. And so I'm blowing up noise. There wasn't signal here.
So there's nothing to be read in that if you follow the lines from the bottom up and they're perfectly straight, and then you see where
These?
the first wiggle occurs. Now start from the bottom.
Yeah.
To the bottom. You can kind of trace out and almost...
This.
Yeah.
Yeah, that's basically me where I started collecting data. And we wanted a prettier plot, so we drew a zeros. I could, you could turn that off. That's right. But this is the P wave. And then you, around here, you hit P wave diffraction. And so there's some noisy stations here, but you can see this guy kind of continuing. And double P. Well, actually, so we make travel time curves. I didn't put them on top. So you can make predictions of as many phases as you want and get some of the exotics in there and core paths. And you actually see some of these guys. Here's the SH. So this is low pass filtered. And so the P wave is somewhere in here. And then boom, this is the first arriving S wave. And so you can see, look, this is and this is just like brute force, quick, dirty plotting. But this, you could see the core reflection here. This is SCS. This is the little s SCS. So it went up from this 348 kilometer deep earthquake, bounced off the surface, went down and bounced off the core. And that's that one. So almost every phase has something, a couple hundred seconds behind it following, and that's the one that went up and bounced off the surface. But check this out here. That's double SCS. It goes core back to the surface, core back to the surface, and here's a surface component up here. And you can see up here is the last one of these that's made my plot. Here it's actually quite strong, if I'm seeing this right. So you have SCS3, or SCS, 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 and it looks like I'm off the surface. So making plots like this, it was the first time I noticed. You can see SCS bouncings up to like 6 or 7 for strong earthquakes. And I've been telling people here, fold these into tomography, you can better image the southern hemisphere or attenuation, because these guys spend so much time in the mantle, they get broader and broader. Yeah, Rosalind. When you overlay things, this is the prediction now. There's SCS2, SCS3. Looks like the surface thing is in there for this time. So it's kind of like, I could probably show you a crystallographic structure, and you're like, oh yeah, that's and I'm like, Okay, so that's global broadband data. I was going to show you some high-frequency data from small aperture arrays. And here's one in Australia by Sebastian Ross. These are like 1 hertz data, so 1 second periods. Bunch of Fiji Tonga earthquakes going down as an S wave, converting at the core to a P wave. And he was after interesting conversions and reflections that you get if there's an ultra-low velocity zone. And basically my one slide of this kind of data is it looks like this. There's some 20-ish stations at this array. If there's no ultra-low velocity zone, these little guys, something bouncing off the top should get there before something going through and bouncing. And even something going off the top, converting to a P wave, so this gets a little head start. P waves are faster than S waves. That should get there before. So you can, that means if I have my core reflection, it's very clear here. Now look at the time scale, 2 seconds, so this has been filtered, so a 2-second energy. There's not much coherent for this earthquake in front of these guys. But then you can go to this other earthquake, and it's bouncing off another spot, and it does, well, there's some energy here. Now, if you're not a seismologist, you might be like, that's all crap. But I believe this. But actually, I don't know, hopefully my seismology colleagues would say, like, no, there's something here that's not here. Definitely in this one, these are noisier because this earthquake just wasn't as strong. But there's something here. So what you do is you can just linearly sum these, or you can get detailed about it by beamforming, by summing this stuff in a grid search. Where's my energy maximum? Looking around. Oop, there it is. Add them along that path and time shifting, and that's what is done. And really enhancing signal to noise ratio. Nothing, something, definitely something. And that's most of the high resolution, ultra low velocity zone imaging is done this way. And then you go into the prediction realm to try to make a model. Yeah.
What is along the way, like I think he said, we assume that the set B is almost a sphere, right? But how much so that the topography of the set B will influence it?
So the question is, how much does topography of the CMB affect this? Well, this kind of thing, when you have an extra wiggle, not too much, it'll affect it for sure. If I here's my CMB, and the table is my CMB, and here's my reflector. If I'm considering something goes boom, bounces, and then this reflection. Now let's tilt the CMB a little bit, and you could argue that this should be tilted with it because whatever viscous forces are distorting the CMB or distort this. You choose what you want. I don't care. The CMB reflection now that gets you to your station, it has to come off another area. Boom, boom. And maybe this one, if they're parallel, it comes off another area to get you to your station. If it's not parallel, they could be offset a little bit. So maybe the paths, maybe our interpretation of where things are hitting and bouncing are a little bit offset, and the times are a little bit offset. But it's not going to affect the positive identification of something that reflected energy. It will affect travel times, and so our mapping of the thickness of this thing will be wrong by a little bit, but not, these are things that you're imaging that are 10, 20 kilometers thick, so you'll have a couple kilometer error. Yeah, Michael?
When you look at something like that, presumably you can use other phases to test this hypothesis interpretation, like SCS.
Yeah. Yeah, okay. So the question being, you can look at other phases, is that right? Yes, you can look at other phases. The challenge is, okay, this spot, these are bounce points of these earthquakes. Now, this path of SCP is asymmetric because it turns out that when you convert to a P wave, it has different velocities. So my Snell's law, S velocity in, P wave out. So if I am lucky and I have earthquakes over here, then I could use my symmetric SCS to hit that point, or symmetric PCP to hit that point. If I have earthquakes closer, then I could use some SP diffracted KS. So there's a challenge to hit the same spot with the same phases because they hit different things. People are trying to do that, and there's a couple places where you can do that. But it's a geometry challenge.
There's some geochemical grumbling here. What is PREM?
I couldn't tell. Your pitch went up, so it made it sound like a question. But the words by themselves were a statement. Thank you. This is a debate, not a debate, a discussion that is very fruitful.
The question I didn't.
Oh, I'm sorry. Okay, the statement, Ed, there is some geochemical grounding for PREM? Grumbling. Grumbling. Oh, I thought you said grounding.
You didn't define what PREM was.
Okay. I'm trying to think if I show the model yeah, so it's preliminary. Sorry, geochemists, forgive me. preliminary reference Earth model that was many types of... Pardon me? That stands for ED. And it was it was a vast, significant update of seismic properties versus depth in 1981. Before that, it was like Jeffrey Bullen's, and there were these other models of seismic properties with depth. And PREM also gives you the P or the S attenuation predictions, and some even anisotropy in the outer mountain. So it's like we make predictions, and we often start with PREM. There's a couple other models that people use, but for travel times and synthetic waveform predictions, it's a one-dimensional radial Earth model for the seismic properties of the planet. Pardon me, Barbara?
You mentioned that one of the authors is in the room.
One of the authors is in the room. I will reveal this author if there's time. I will get to the slide that reveals this author. Question in the back?
I'm wondering why you don't do that. I think as PCP say, if they will come to the same point.
We do. Actually, this is there are what I would call data junkies. So any earthquake that happens, we go and we look at it, and if you see nice data, you're like, oh yeah, you grab it and you. So we have a closet full of all these data. So we use those. Definitely, SCS and PCP are used. I just picked this example because it was on my laptop. Okay, so what do we actually measure from these things? Travel times, amplitudes, the spectra, particle motion, wave shape complexities, sometimes things you don't predict. Now this is just a very quick slide sequence because I'll talk more about this next Tuesday. I cherry-picked an earthquake that New Year's Day. Now I'm showing S waves in the transverse component of motion. And this is just a couple degree distance centered around the S wave arrival here, showing up around relative to the preliminary reference Earth model predicted S waves. And actually, this is impressive. These are what I would call good data. Now, one person's good data is another person's bad data. One person's noise is another person's good data, depending on what you're doing. We doing these observational body wave things, what we typically call good data, if you're looking at single seismograms, you don't want to see a lot of energy in front of the pulse of interest. These are displacement seismograms, so this is instrument deconvolved. This is actually ground motion at these sites. So boom, the thing comes. The core reflection is robust in there. And then this is a deep guy, which I was showing you stuff from this earthquake before. You have the surface reflection. These guys are flipped in polarity to preserve the boundary condition. Here's the SS wave, boom, between source and receiver. So I'm going to zoom in right around here, those guys. And you can see, well, that's interesting. These guys don't show up at the same time. Now, my tutorial, which gives you the tools to make these plots and stuff, is intended for us to like look at this and say, well, these guys might be coming to the going from the earthquake in totally different directions. And so that's something that would be your first thing to, before you try to, write home about this. And you're like, wow, that's, 5 seconds of an anomaly. And so somewhere in the Earth, one of these guys was delayed relative to the other guy. Here's another case of the SCS wave here. This peak is ahead of that peak.
So, as a geochemist, mass spectroscopist, we think about these things. What's wrong with the instrument is one of the things I'd say. And so what I see here are two different wave patterns that you're pointing out, and they're probably, longer or odd. And then you said it was 5 seconds, so that can't be instrument.
Okay, the question is, could this be something to do with the instrument? And that's actually a really important question. Sometimes there are instrumental errors. Or the instrument's fine, but I'm sitting on some sort of structure where the cone of energy from that earthquake really did delay, has nothing to do with my Earth interior volume of interest. You can get around that by looking at lots of earthquakes, and so a careful seismologist would be paying attention to that site. Okay, so I guess we started a little after 10.
Isn't that also one example to emphasize why you want to look at differential?
Yeah, so Gabby's point is, isn't this a good example as to why you would look at differential times? And that is one of the reasons. You're trying to minimize error where the paths are really close together and experience the same anomaly. But anyway, I just wanted to show you can look in raw data and see interesting travel time phenomena. You can see straight away interesting amplitude phenomena. Here's the S wave and the S wave. Here's the SCS wave. It looks delayed in this, and not much there for that guy. So that's interesting. Is that radiation pattern? That's something you would check. Frequency, you could see it right away, like, why is this S wave? This is the same earthquake. The same earthquake should give you the same spectra, right? This guy is fatter than this guy, and so there's something interesting there. I'm not really modeling, I'm not giving you answers for this. I'm just saying these are raw data observations. This is the Earth. Sometimes there are things that you don't expect. There's no predicted arrival here from standard reference Earth models. This little wiggle turns out to be, well, you might see like, wow, you picked a random wiggle. Here's one. But looking at a lot of data, this was Thorne-Lay's thesis to explain a D double prime discontinuity. And this, there are people in this room who've studied that. So anyway, you could. This is just 2 degrees of data of this earthquake, that of which I showed you 900 something seismograms, and we have hundreds of earthquakes. So the Earth is rich in information. Nobody said anything about like, well, what's all this other stuff between these lines? I mean, so the Earth is making interesting energy. So I'm going to quickly whip through. I'm not going to talk about how we do analyses. I'll do that in the Seismo 4 lecture. And I don't want to, I don't want to go too long, but I think just really quickly I'll present a couple sort of results, interpretations. Some of these are broad brushstroke, like for example, these are things that Barbara will perhaps cover, where the heterogeneity spectrum, the heterogeneity amplitude in the top and the bottom of the mantle are different from the middle of the mantle. I was showing some examples from the deep. This is also, where has anisotropy been advocated? Inner core, bottom of the mantle, crust, upper mantle. Some people have argued the top of the lower mantle. It's quite debated. Let's look at this geographically really quickly. This is a slightly older figure, but what it's showing you is isosurfaced velocity at this value for 5 models I can count. And this is basically just rotating the globe 90 degrees in each row. So okay, here, this Berkeley model, boom, this is centered on the Pacific, Americas, Africa. So the first order thing is all these models. I mean, this is pretty remarkable that you have this degree 2 red stuff. And these are the LLSVP, large low shear velocity province. I didn't come up with that name. So here we are looking into the planet. Here's the core, and here's the African and Pacific anomaly. And I contoured this so the blue stuff is, minor. Okay, an interesting thing, and I'll talk about this next time, is there's been some 12 or so studies that have found sharp boundaries to these red things. The sharp, I'll make a comment on that in a little bit. So it's hard to do that thermally alone. Bill?
Just go back one diagram. As a geochemist, faced with an interesting issue, collaborating with geodynamicists, we chose one of these. And we said, okay, we're going to use that image of an LLSVP, and then we said it represents this mass and this concentration of elements. And then a seismologist says, oh, you shouldn't have used that model. And so as a geochemist, I go, one of those 5 different models should we use?
Okay, the question sort of relates to being a geochemist, and you pick a model and then a seismologist tells you shouldn't have used that model. You have to choose your friends wisely. Yes.
But is that possible to make seismic wave reflection?
Is it imaged using seismic waves with reflections?
LLSVP can be resolved by a reflection of seismic waves on the.
Oh, yes, yes. Actually, there are some blue areas that are extremely well sampled and even better than the red areas. So these images, I think, are robust. You could start a debate about what little features. And one of my points is the little features matter if you're doing a regional high-resolution body wave study, because let's say I'm sampling this spot. Well, there's nothing there on that one. I'm on the edge of something in here. I'm in blue on this one, and I'm in blue on that one. So these are long wavelength models, and I ISO contoured, and so it's a little misleading to look at these features exactly, because this is just fitting a sheet at some level. And so it implies something's there and not there in some models. I mean, that may not be. Yes?
Sorry, to get back on that point, Bill's comment, is it possible to make another column that shows the average setting and then try to find the standard deviation from the spread of the model?
The question is, what about doing an average and looking at the standard deviation? Funny you ask. I stuck a slide in the end of my talk, which I wasn't going to show because there's some volatility associated with it, where I reparameterized tomography models. I think I did this in 2006, and so I had 12 models at that time. These are shear waves and P waves, and I redid the velocities from 0 to 100. I divided all, because how do you deal with amplitude? So you could do it as spherical harmonic and do spherical harmonic coefficients. I chose a different way. I divided the Earth up into 40,000 equal area cells, and then I organized them from 0 to 100. So 40,000 numbers between 0 and 100, And then I just said, okay, where's the 10% of the surface area of the highest velocity on the planet? I can compare from this model to this model. So the highest and lowest velocities. So in this kind of plot, and so I took the mean of all those models. So 0 to 10 is the 10% lowest velocities on the planet. I did it shell by shell. This is the base of the mantle. And so this is the average. This is exactly what you asked. I did it because I was really interested in how alike are these highest and lowest velocities on the planet. I was after the subduction zones and the termination of the evidence of slabs in the mantle, so I was doing it this way. You could see that the models are in quite good agreement in the degree 2 things. And my query about this is like, wow, is it like everybody has long paths through the middle, and so we might smear things equally and do well here, but that's not exactly right if you're including modes and stuff. This also shows the like what does this standard deviation really mean? But you could, in a relative sense, look where things are in more agreement or less agreement. And I assume, Barbara, you talk about the Perm or Permian.
I think maybe Adam will.
Oh, Adam will. Great. So, and they do this a different way, using cluster analyses of where things agree and don't agree. To me, this is it's really interesting. I did it, and I was intrigued by it, and I left it alone. Okay. So I have to sum up pretty quickly. So I think I'll. No, I choose your friends wisely. I thought I expressed that. Okay, anyway, Alan McNamara with Qizhi Zhang did a very cool thing of imposing plate motions, and others are doing this as well at the surface, and it's viscous flow, and Earth-like properties aren't exactly achieved or even known in these models, but it was a remarkable comparison. This is seismic tomography here, and this is an initially uniform dense layer in the bottom of the mantle that will deform according to convection when you impose Lithgow, Bertoloni, and Richards plate motions at the surface. Is that this stuff responds to the downwellings and gets swept underneath upwellings into first order, it agrees. And so this, along with seismologists finding sharp edges around these things, is, I think, the gas in the engine of the perspective that the LLSVPs are chemically distinct. I'll talk more about this on Tuesday. There's others who have made notes that, hey, if you take, this is Norm Sleep's hotspot catalog and just drawing straight lines to the bottom, only showing the low velocities, that hotspots to first order are more likely to overlie LLSVP edges than centers. And other seismologists, this is Wen in the African anomaly, have made this note. And then more recently, the song we've heard sung is the Burke, Torsvik, typo, et al. Co-workers with reconstructed large igneous province locations overlying LLSVP edges, kind of supporting a chemically distinct origin of these things. So.
But that analysis also assumes that these things have been in the same place for the last 200 million years.
That analysis assumes that these things have been in place, according to these workers, 200 million years. My take on it is these things have been in place long enough, sort of stuff that erupts to get to the surface for there to be record of it, to be down there now. So 100 million, I don't know. That's an important question to pursue. Dynamically, with time-varying subduction currents that are viscously maintaining the shapes of these piles and moving them around, are they going to stay in one place? There's a lot of questions associated with that, like, okay, when you build a supercontinent, do these piles really go into one super pile? And then how do they go back?
I think the edge of this LLSVP is quite sharp. I'm wondering whether the top and the cap of the LLSVP is also circumference.
I'm going to talk about that on Tuesday. I argue, yes, if you can image it. And by how can you image it, you need the morphology to be such where you can get a reflection off of it that you can understand. Because if it's all crazy, it's harder to get coherent seismic energy. I have like about 4 slides left. I'm just going to breeze through them. Just say there's a lot of regions where seismology has found this reflection in D double prime. Now we're at the bottom, few hundred kilometers of the mantle. This is consistent with the perovskite to post-perovskite phase transition. Different methodologies have seen this using the type of ways where you look at specific wiggles like I showed you and you model them in a forward sense. You get a variety of models from different regions. You could do waveform inversion, this is pioneered by Kawai and others, where you actually get similar stories with different details. But anyway, the evidence for a reflector appears robust. You can go on a smaller scale, that's hundreds of kilometers. Now you go to 10 kilometers at the CMB, evidence for velocities reductions, possibly density increase. And I'll, since people had encouraged me to, I will talk more about this on Tuesday. But we end up with maps of ultra-low velocity zones with the suggestion, okay, the red areas are where they're advocated in studies, blue areas where they're suggested to be absent on top of a tomography model. So the suggestion is, hey, maybe these things are preferentially located near perimeters of large, low shear velocity provinces. This kind of leaves one wanting for more data coverage. So maybe out of this workshop with these tools I share, you guys will want to do seismology. On the other side of the boundary, there's, this is from Helfrich's recent paper, there's, and for some time there's been evidence for velocity reduction. How do you do this if you're exsolving things from the core or double diffusive chemical reactions, whatever you want? One would think that the velocities would be higher with the lowered density. And so this, tens of kilometers, a couple percent drop. We did the same thing like 15, 20 years ago. And there's our little curve, which actually agrees quite well with George's, but he chose to ignore us. And the bottom...
Ignored a paper by, I forget the first author name, I guess is from Canada. And they did, it was published also. They actually thought they also had seen S4 KX, and they felt the parameter is just okay.
That's right. So Adam mentions a paper there's a couple that had argued that PREM is okay here for one particular study, and so I actually I'll talk about this a little bit on Tuesday. My current view is this may be downward projection of mantle heterogeneity in D double prime. Tell me about it. Okay, there's very quickly, this is the bottom of the core. Here's the inner core, outer core boundary. There's perturbations from PREM on the above and below it. This is by you et al. Paper. So this is another region of interesting stuff that relates to how the core may work. So I guess in summary, this is my isotopic diagram, Bill. So there's a lot of paths through the Earth. When I was a graduate student, at Caltech there were these large travel time curves where Gutenberg by hand had written little X's of things in observations, and these little X's of observations of unknown pulses show up on lines, and then you figure out where they go. You have paths in the interior. And so there's a richness in the wave field that is, even as of today, untapped to some extent with these large high-density arrays. And being a bit provocative, I didn't really talk so much about what seismology can and can't do, but many of these seismic waves and analyses can help us get at, and researchers are pursuing these things, the water budget, how the outer rigid part of the planet moves, breaks, exchanges with the insides, and this is more of a evolutionary pathway, and so on. Many things here that we can do. But in order to do it, I'm just going to leave some parting comments up here, is you can't study everywhere with these kinds of waves, and you need a close-by reference phase. And I didn't talk about resolution here. Here's one issue. We can't really say something's a perfect discontinuity. It depends on the wavelength of the wave, but there's always a transition depth, if it's a layer or whatever, that can often give you the same answer, and that depends on your frequency of wave. More data is key, and there are some, and Adam advocated this thing in our community that I hope is getting traction, this idea of really large arrays and a network of them called array of arrays. Because just like astrophysics, data is key. The US array, HiNet in Japan, there's a new China network. The more data we have, we start seeing these things in greater focus and seeing things we didn't even anticipate. So this is a little soapbox I got on at the beginning. These high-resolution body wave analyses are part of these efforts to image a planetary interior. And in the case of the Moon and hopefully Mars, where we can get sensors, you need this to say something about the interior, to get at these evolutionary pathways. Some of them, you never quite tape it all together, but you need this information. And so I'll present more of this in my Tuesday lecture. Thank you.
Can you discuss the relationship between the LSEP and the ULVs? Is it just a matter of magnitude? Is one a subset of the other?
Yeah, the question was, can I discuss the relationship to LLSVP to ULVZ? Let's see, do I have internet connection? Do I dare try? I won't. Yes, the LLSVP is quite large in, let's see, in one of these random talks I show a figure. This is dangerous. What did he say at USC? I'm searching for kind of I avoided it in this talk on purpose. A synthesis figure. Probably have one. The Moon. Oh, you loser. Let's see here. Well, this will work. The LLSVP is continent sort of scales, thousands of kilometers laterally and hundreds of kilometers vertically. In some cases, it might be 1,000 kilometers high. People have advocated the African LLSVP really sticks up. It's a super plume in action. ULVZ, I drew this in PowerPoint. It's kind of lame. But the ULVZ is tens of kilometers max, maybe more, at least in what has been resolved image-wise. It could extend up, and we're just not getting those skinny parts. Geographically speaking, its relationship to the LLSVP is a dynamically consistent scenario. If ULVZs are at the base of the mantle, then plausibly dense, and some seismology has argued that they're dense. In the dynamical calculations, if the ULVZ has some appreciable viscosity, it'll migrate along to the margins. And that has been the argument in some of the seismic studies, that you find ULVZs on the margins of LLSVPs. Doesn't say what they are. They could be partial melt of the LLSVPs, because we predict the hottest rock in the mantle on Earth is at the margins of these LLSVPs. You're dynamically subducting, so you're a lot of heat flow, and so you're just bringing stuff here like that. Now, the ULVZ? No, not necessarily. If the melt is denser than the solid phase, it can, and that's the hottest part of the LSVPs. That's where it could be. Now, how do you get the top of the ULVZ to be sharp if it's partial melt? Some folks have fashioned some arguments for this. But not all ULVZs apparently are created equal. There are some that don't have a huge shear velocity drop, and so that could maybe they are compositional. My preference is to think of them as another entity. Otherwise, we wouldn't see them outside of the LLSVPs. So. That. Oh, Bill, thank you.
Your last point, conclusion, is talking about the future of seismology. In fact, from a perspective that I have, let's say, understanding the bulk composition of the Earth and the mantle, one of the things I'd also like to encourage the seismology community is also look at non-things.
Look at what?
Non-things.
Yeah.
So by that, I really specifically mean perhaps advances could be made where, say, out in the middle Pacific, where there's no super plumes and no funny lithosphere, no pond something deeper above the transition zone. So it just what might be called a vanilla flavored mantle. And baseline of reference model. And actually really pin that down and say, this is the value of the ambient background mantle where things are not. And the uncertainty is really small. And then we turn to our mineral physics colleagues and say, can you tell me how much olivine is in that portion of the mantle?
Okay, so for those who didn't hear him, Bill's comment was that as we move forward into this next generation with greater, more sensor networks, we should image the areas without these terrific, dynamically sort of related structures. Okay. However,
but don't forget to add, so we can feed it to the mineral physics.
As it should be. So the mineral physicist could come to the door of the seismologist beckoning for information. No. There may be a problem, though, because I've often thought, like, if you had a deck of cards and tossed them from space and they landed on Earth, and you took a 50-kilometer by 50-kilometer piece of Earth, wherever the cards landed, what are your chances of finding something vanilla? I guess if you appealed to the abyssal plains in the Pacific Ocean, you might say, this really is, this region here, between Hawaii and the Cascades, looks a lot like this one between Hawaii and Cook's Island with nothing going on. I don't know. Actually, I'm not so sure. And in fact, I was impressed maybe 10 or 15 years ago that every high-resolution study of the deep mantle, now, this is again subjective. What do I mean by high resolution? I won't spend time. Has found something interesting. So, I mean, maybe this is for the dynamicists to answer. Can you have a region in the lower mantle with big structures and subduction carrying stuff, circulation, that is vanilla? Do you always have chocolate chip? I don't know. Yeah.
I'd like to comment on this because this touches upon a discussion that is more and more prevalent in the community, is that, in fact, there is the 1D reference model. The 1D reference model, like PREM, is really not necessarily representative of anything, any particular mineral physics, whatever, composition. And that you really have to look at, because the Earth is 3D, you really have to look beyond that and construct a 3D reference Earth model, where, in fact, we know that if you look at the fundamental value, you see those LLSDPs, you really see LLSDPs and no LLSDPs. So you see two types of regions, right? So can we constrain the seismic parameters in these two regions, and then look at those separately to look at composition? In the upper mantle, we can do that also. We can regionalize, continents, oceans, and then slightly more. But that is really the trend now, is that interpreting the 1D model does not really make sense necessarily.
Yeah, so Barbara's comment about 1D reference structures, I completely resonate with, because your reds and blues are determined by your reference structure. What if we gave you a velocity map without reds and blues, old school black and white with the contour lines and numbers, and then you guys tell us what kind of rock these shapes might be, which are influenced from the geodynamics knowledge base of viable temperatures of the things going down and coming up, also from the geochemistry. I think it's a tough deal. Like, in fact, the PREM model, and I brushed over the slide. It was Jawanski and Anderson, 1981, which it has more references than probably all my references put together times 10, easily. I mean, it's amazing.
You're too shy. If you have your references, it could be.
No, I will bet you a good bottle of wine.
Well, we use about half of them because PREM is used generic.
Oh, this is true, yeah.
Without a specific reference.
Yes. Hera.
CMT solutions.
By the way, that's the moon. So the base of PREM, as I understand it, you and Don Anderson had discussion of, do I put in a discontinuity or not put in a discontinuity, and so there was an agreement to change the velocity gradient, a new polynomial from 150 kilometers above the CMB. If you take that out and continue the polynomial from above it down and say that has something to do with the adiabatic gradient, then most of the base of the mantle becomes red. And there's two little blue spots, one beneath the Caribbean and one beneath Eurasia. Now, this is just kind of fantasy playing with numbers and may not have anything to do with the Earth, but Barbara's point's a really important one. Let's see. Sorry. Rosman.
Yes. So I have a question about the noise. Where is the noise coming from? Is it something in us? Is it something due to the machine, to your seismometers? And can you use this for something?
Okay, so where does the noise come from, and can you use the noise? The noise is, like you saw those wave propagation calculations, the noise is from seismic energy going all through the medium. And the medium of the Earth is not this platonic, ellipsoidally layered thing. It's full of heterogeneity. So it's earthquake energy that's rattling all over the place. And yes, you may talk about this, I hope, or maybe not, but the noise has been used to image structure, as well as to talk about when earthquakes aren't there, there's noise. And Barbara and Shiro Tanimoto have some, and others have some paper on earth hum, and which is really fascinating. So the noise it's an important part of energy that some seismologists are using, which relates to my comment of one person's noise is another person's signal.
But most of the noise, the background noise that is not earthquake generated, that is not signal generated, comes from the oceans. It's in various frequency bands. The microseismic energy, for example, is a peak of noise around 6 to 7 seconds. And that is why also we have a tendency to filter data either to longer periods or to shorter periods, because we want to avoid this peak of energy that is very, very tall. But they also have noise coming from the oceans at much longer periods. And as Ed said, either you can study the noise for itself, or you can use it to study structure.
Yeah.
Maybe I'll say a few words about that.
Yeah. Jackie, did you have a question?
Yes. So I have a question for seismologists in general. As a mineral physicist and geochemist, often I have to choose to reference a 1D or 3D model. And there are different 1D models now, PREM, AK135, and I think you showed another one, DM or something. And for the tomography model, there are even more options. So that makes it difficult because you don't want to cite all of them. It's kind of redundant and they are a little bit different. So is there any plan for seismologists to come up with some kind of model for people outside the field that is robust feature common to all the models? Or maybe when you're looking at the core or looking at versus mantle, you choose this model versus that model.
So Bill's question has come back to haunt me. So the question was, as a mineral physicist, geochemist, and how do you move forward in choosing the right 1D or 3D model? And is the seismological community trying to come together and have a reference 3D model? There have been efforts to move towards a reference 3D model, and I think those are moving forward. I think there are seismologists. I read a proposal on one of these that I gave very high marks. I think it's an admirable effort to bring people to the table to do such a thing. Now, which model do you choose? I think this depends on what you're after, and how could you know? Now, how could you know which model to choose, not what you're after? I think depending on the nature of what you're looking for, if you're really interested in the details of a model at a specific location on the planet, and you're working with someone who you really want to say something about the asthenospheric structure, as you're going into this one particular trench because your colleagues have imaged something, I think you have to look at all the models. And you have to understand how the models are made and what those models are sensitive to. And you may need to even talk to these seismologists. If you're talking about, okay, I want to give a mineral physics explanation for what a LLSVP is, and I said, I don't know that it's so important which model you choose because all of the models have them. You could play the societal preference game of like, well, who are people referencing these days? But that's silly and arbitrary. So I don't really know. Or you could say, okay, there's this question, I'm going to choose an average model. And so there are a couple studies. I think the most cited one is the Bocci and Becker one, which they've averaged models. It's a G-cubed paper, and I can give you the reference. S-mean. They average all the models. Now, I didn't quite address the question of how do I feel about averaging models. It's depending on what you want to do. I mean, if you really want to understand the Earth, averaging things that are sensitive to different things, I think it probably takes you farther away from the physics of what's making structure. And so you can get into trouble.
I could give one example for S-mean, which is that it averaged models that some of them were the anisotropy in the Earth.
Yes.
And that was completely ignored. So some models were based on data that were primarily sensitive to SV.
That's right.
And some models primarily sensitive to SH. They look different because, in fact, they're not looking like the same thing. You average them, it doesn't mean anything.
Yeah, so that's exactly right. Yes, Gabby?
Yeah, I think that's why it's important to understand that the best representation of the spherical average of Earth compared to other planets, if you want to compare other planets with Earth, the best model to represent Earth still is PREM, because it's a true spherical average of structure inside the Earth. Whether it's physically meaningful or not is another question. But as a reference model for the spherical average of the Earth, PREM is still the best model. Because other reference models, they are reference models, but they are not necessarily representing the 1D spherical average of Earth structure. And that's a very important point to make.
Right, but that's a reference model for seismologists. But for mineral physicists,
yes,
it may not be good enough.
Yeah.
Yeah, but compared to AK-135 or the ISP model or something, this is a seismic reference model, but PREM is the one that represents the spherical average of.
Well, you're speaking like a long period seismology. Because it is true, it's the best model for long period seismology.
PREM
If
has
you
a
study the
1-second
core,
version and a 200-second version.
if you study the core, you will find that AK-135 is a better reference model. That is, your travel times are closer to AK-135.
Okay. Wait. So one more comment, because the author of PREM has a comment. Yeah.
Well, I have a research talk this afternoon which will address some of the issues that you brought up or were brought up by the questions.
Okay. So Adam has a research talk this afternoon. Not to miss, some of these questions will be brought up. Thank you.